Thank you. Thank you so much Thank you for inviting me. I think I spoke at probably the previous incarnation of this seminar series a couple of years ago.
Yes, in the middle of COVID,
everybody was online, so it's actually great to see that this time, the other people on the other end are all in the same room. So
you don't get the cookies. The cookies.
I don't get the cookies, unfortunately, but maybe next time.
Yeah.
Okay, so this work that I'm going to talk about is in collaboration with Vedika Kemani at Stanford. This is the reference. And by the way, there was also a nearly simultaneous work by Yizhuang Yu's group in UC San Diego, which is referenced here. And by the way, yes, I saw on the schedule that Sam Garrett gave a talk a few weeks ago, maybe last month, on topics that are related. As you see, the problem we study here is different. It's a different problem, different results, but many of the ingredients are in common. So maybe some of the things I'll review will be familiar to some of you, but that's okay. We'll do a little refresher and then we'll get to our
new results. Matteo, I have only one request. There are a couple of faculties here, but you should ignore them and really speak to students and postdocs.
Okay.
And don't assume that we remember something from months ago.
Absolutely, no assumptions. We'll start from, as you see, we'll start from the very basics. We'll start from measurement in quantum mechanics. So from the textbook, okay? So I'm half joking, but just to set the stage, right? So we know that the rules of quantum mechanics, at least most of the time, are that quantum states evolve according to Schrödinger's equation. And so this is an equation that has many nice properties. It is linear in the many-body wave function psi. It is smooth as a function of time, and it is deterministic. So in principle, if we know everything about the system, we can predict the evolution all the way into the future. And this is conceptually very nice. Unfortunately, we then find out, when we move forward in our study of quantum mechanics a little bit, we find out that this doesn't always work. There is a whole class of exceptions where these rules seemingly go out the window. And the evolution is, for one, it's random, it's not deterministic anymore. We make a measurement and the outcome can be predicted only probabilistically, but not, the outcome itself is random as far as we know. The process of measurement is also discontinuous in time. So there is a state that's before the measurement and one that's after, and they don't have to be very close to each other. They can be quite different on a completely, both at the level of many-body, observables, locality, and so on and so forth, completely different states. And also the process, if we normalize our post-measurement wave function, we also get that it's nonlinear. So all of these nice properties of Schrödinger's equation are gone, and we have a completely different set of rules for this whole class of processes, which we are vaguely calling measurement, but it's never really quite well defined. And this comes with its own set of rules. However, we then, don't worry about this too much, typically, if we are condensed matter physicists, and that's because most, if not all, of condensed matter physics takes place within the first set of rules. We are typically concerned with ground states or thermal equilibrium states of a Hamiltonian, or we're concerned with non-equilibrium problems that are like quench dynamics. We take an initial state, we put it out of equilibrium, and we watch it evolve under Schrödinger's equation for some given Hamiltonian. So all of these things are completely described by this first set of rules, and then measurement only comes in as a way of looking at it, of figuring out the observables we need to describe it, but they don't directly come into play in the physics. However, this is set to change, or is already changing with the introduction of a new family of quantum technologies, which we can collectively refer to as synthetic quantum matter. These are a whole range of platforms, from superconducting qubits to ultra-cold atoms and trapped ions and many others that I'm not listing here, that, what they have in common is that they're being developed for, quantum computing or quantum simulation. And that requires you, in these technologies to have a really, really sophisticated degree of control and measurement capabilities. And in particular, this opens up the possibility of doing kinds of physics where the measurement and interaction with the observer is much more important and much more central than is typically the case in condensed matter physics, or has been the case on more traditional kind of, standard matter, not synthetic matter. And in particular, this shows up out of equilibrium, as I'm going to kind of argue next. And to make that point, again, let me emphasize that these systems are being built for quantum computing, right, essentially. And the standard model of quantum computing that I'm sketching here is that of a circuit, it's a so-called circuit model of quantum computing, where we have qubits that are two-state systems that are represented here as these vertical lines. In this diagram, there is time flowing from the bottom to the top. So these lines are the state of a qubit traveling through time. And these blue boxes are so-called unitary gates. So these are unitary interactions, so two-body Hamiltonians acting for some amount of time on two qubits locally. And so with this interaction, the two qubits can become correlated or entangled. And as we stagger the interactions in this fashion, we get a correlated many-body state at late times. Okay, so in quantum computers, this type of controllable interactions are used to implement, quantum algorithms, particular computations. But at the level of physics, this just means that you have an extreme freedom to cook up arbitrary time-dependent Hamiltonians, essentially. So you're able to drive your quantum state in, weird ways that are not normally possible. At the same time, we also have, these drive capabilities are very advanced, but they're not perfect. So we will make errors sometimes. And an error you can think of as some perturbation that happens at some particular location in space and time during our computation, but also as a kind of imperfect isolation of our quantum many-body system from its environment. So we can think of this as also being exposed to a thermal bath, right? And this brings in another set of interesting open system effects that aren't captured just within unitary evolution. And then within quantum computing, at the end of the day, we want to get a result. And so we have to be able to go in and read out the final state of our system and convert it to a string of bits. So we have to be able to make measurements that are beyond the usual ones we make in condensed matter physics. For example, measure the conductivity of a sample. There is only one number that tells you about the collective behavior of many degrees of freedom. Here, we actually want to be able to measure the individual degrees of freedom that make up our many-body wave function, one by one, essentially. And furthermore, we don't just want to read out the final state, but eventually, if we are to be able to figure out that errors have happened in the computation, we also want to be able to make these measurements as we go. So during the dynamics, not only at the end. And once we detect the errors, we would also like to be able to correct them. And so we have to be able to take this information from the measurement that happens during the dynamics, process it in some way with classical simulation, computation of various types, and then potentially feed it forward in the future time evolution of the system, for instance, by controlling the sequence of unitary gates following this step, okay? So this would give you quantum error correction capabilities, which are, a goal for the future of these systems. So again, I've motivated all this in light of quantum computing, but even the angle I want to take here is that these are really particular ways in which a quantum many-body system can evolve. So very general kind of time evolution that is that brings in all of the rules and all of the ingredients of quantum mechanics. Okay, so unitary evolution, measurement, open system dynamics, and all that kind of comes together in different ways in these systems potentially. And this opens up, a lot of possibilities, but in particular, from the point of view of condensed matter physics, one can ask, is any of this universal? Are there universal behaviors that can be realized or discovered in this very far from equilibrium, very general type of evolution that becomes possible here? Okay. So this was just a very general introduction to, kind of a whole field. And, obviously today I'll only talk about some very narrow subset of this whole field. And I'm sure many other talks that have happened in this series have addressed other aspects of this. But for today, we'll talk about two topics and how they can come together. The two topics are monitor dynamics on the one hand. This is dynamics where measurements come in throughout the many-body evolution, as I was sketching earlier. And this gives rise to some interesting non-equilibrium phases and phenomena that I review. And then the second topic is so-called classical shadows, which is a fancy name for a protocol for trying to learn many properties of quantum states from a relatively small number of measurements. Okay. And we can, in this work, we bring these two themes and two topics together, and we find some new phenomena, in particular, a phase transition in one's ability to learn about a quantum state from monitor dynamics. So I will tell you what this means in the rest of the talk. Okay. So let's start with a bit of a review on monitor dynamics that features measurement as we go. Okay. So again, I'm sketching it here. This is the same kind of circuit diagram that I had earlier. Now I'm thinking of an isolated system. There's no there's no noise at this stage. There's no open system effects. There's only measurements that are performed, intentionally by, an experimentalist, okay, that are happening throughout the evolution. The idea is that normally, in the absence of measurements, kind of chaotic unitary evolution would tend to maximize entropy and get you to thermal equilibrium, at some high or infinite temperature. But in the presence of measurements, we keep resetting in some way part of our state to some kind of simple non-equilibrium state. For example, if we measure a qubit, now the state of the qubit is either 0 or 1, and it's disentangled from the others. And so we kind of, by repeatedly doing this, we are preventing our many-body state from reaching equilibrium. And we keep kind of bouncing around the Hilbert space as we go and as we continue to do this. However, even though individual states never reach an equilibrium value, as it turns out, there is a whole ensemble of these states that we generate as we make these measurements. And those ensembles can reach some, universal behaviors. In particular, as a function of how frequently we measure, so how many of these measurements we have in here in the bulk of this space-time. Let me parameterize that with a probability p between 0 and 1. As a function of that, we can have sharply different phases in the structure of entanglement of these late-time states that we prepare. So in particular, if the measurement rate exceeds this threshold pc, which is some number that we can in principle compute between 0 and 1, then we have a so-called disentangling phase. So the late-time states have very low entanglement. In particular, they have a vanishing entropy density. So if we take the entanglement entropy per unit length of a subsystem, we get a number. That number goes to 0 in this phase. And then as we tune the density of measurements below this threshold, we enter a so-called entangling phase in which this density becomes non-zero, and it sets in some non-analytic way at a critical point. Okay. And then eventually, as we take p all the way to 0, we recover unitary evolution without measurements. And in that case, the late-time state achieves equilibrium at the maximum possible entropy. So the entropy density goes to 1. Okay. So let me say a little more about how to think about this kind of these phases, this phase transition. The idea, without doing any math, is just think about this process as generating some network or web of quantum information in space and time. So for those of you who are familiar with it, I'm thinking of tensor networks, but even if you're not, just think of a network of correlations in space and time that describe how different qubits at different positions or temporally separated positions are or are not correlated. And it is that as you make these unitary interactions, you can generate these correlations between neighboring qubits, and these correlations also propagate through time. And then as you make measurements, which are these, these boxes here, these are capable of cutting some of those connections, disconnecting the past from the future, or disentangling different spatially separated subsystems, and so on and so forth. So the question is, this network of information that we're creating, does it remain connected, or does it kind of break down into many small pieces as we build it up with unitary interactions and these measurements? This is a bit of a classical intuition. It's similar to percolation, and that is not a quantitatively exact thing, but it's probably good enough to have in mind as a kind of intuition. So think of it as a percolating or non-percolating network of information. And this manifests, if you look at correlations between different types of subsystems. So for example, if we ask about entanglement between subsystems A and B in the final state, so I'm thinking of time as going from the bottom to the top. So the surface here at the end, that is my final state. So if I take this entanglement entropy, I get the behavior that I was mentioning earlier with this transition from a so-called area law for entanglement, where the entropy density goes to 0, to a volume law. And again, you can think of this as the nature of the structure of this network. So in the area law phase, we have a network that is disconnected into small pieces. So there is only entanglement about the boundary here. There is short-range entanglement that only qubits near the boundary contribute. And in the other phase, we have a connected network. And so in principle, all the qubits in the bulk of these subsystems get to contribute correlations and entanglement, and we get a so-called volume law, a finite entropy density. However, once you have this picture, kind of space-time picture in mind, then there are many different manifestations of this phase transition that all become equivalent, all become different ways of looking at the same thing. So a different phenomenon that was discovered about a year after these kind of first papers in 2018 is asking about a different configuration of systems, in particular, the correlations present between a system in the past and one in the future. So subsystems that are separated in time instead of space. And this you can interpret as a phase transition in the amount of memory of initial conditions in the system. So here, in the phase where the network gets disconnected, we're essentially quickly forgetting about the input state and getting some final state that is independent of the input. Whereas in the other phase, there is information about the input state in A that you can in principle recover from the output state in B. This was made mathematically precise in this paper by Gallants and Hughes in 2019, where they present this in the language of dynamical purification. This means you send into this process a mixed state, for example, a completely mixed state, identity matrix over Hilbert space dimension, and you ask about how mixed is the output state. And in particular, you find that in one of the phases, the phase in the disentangling phase, the output state you get is actually pure or near pure. So this whole mixed state you sent in gets collapsed down into one particular pure wave function, which means that information about whatever you might have encoded in here gets overwritten. So this mixed state means qualitatively the mixture of all possible states you could have sent in. So an average of all possible messages you might have sent in. And if the output is a fixed pure state, that means that no matter what you sent in, you will get that same output. So the information you sent is overwritten and lost. On the other hand, in the other phase, there is some mixed, some entropy of this state that persists up to late times. And so we can call this this phase mixed, this phase pure. Okay, but these are, again, different ways of looking at that same phase transition induced by the measurements. So if there are any questions about this at this stage, please feel free to interrupt.
Could I ask a question?
Yep.
Well, it's a two-part question. So I imagine from the way you're describing it that the critical point, the critical value of this measurement probability is the same for these two cases. And what I'm wondering is, do we have an analytic handle on that number?
Right, that is a great question. So yes, it is the same for both of these, because as I was hinting at, this is really one bulk phenomenon, and then you're kind of attaching different boundaries to it, but they pick up on the same transition. The handle on the number we don't have, because the number itself is non-universal. And so it's, it varies with details of the model. We have a little more about universal properties like critical exponents, but even those we don't have, away from special limits, we don't have an analytical handle on, for example, which conformal field theory describes it. So analytical predictions for the critical exponents and all that, we typically don't, away from very special limits, where this becomes percolation, for example, and then we know everything there is to know. But generically, those are not non-generic limits. So the true transition for qubits, for instance, is not well understood.
Thank you.
Mm-hmm. Yeah, thank you. That is a very, very good question. So this is, I was just giving an introduction to these different pictures, and in particular, dynamical purification, which is the picture we'll have in mind for the most part. And then a key aspect of this physics that sets it apart from more familiar types of phases of matter, for example, is that this physics is intrinsically random. That makes it a bit hard to see. The reason is that each of these measurements that we make can have, for example, one of two outcomes, 0, or 1, those are two states of a qubit. And we can, we obtain one of those at random. We don't really get to decide which one we get. And as we, go through this experiment, it's as if we are traversing one particular branch of a tree. This tree contains all possible histories of the experiment, which keep branching with every measurement we make. It keeps doubling in size. And I can write the whole sequence of outcomes I got, and this will get me one of exponentially many possible wave functions here at the end. The problem is that if I just take the average of these wave functions, in this sense here, the stochastic mixture of those projectors, that is basically a thermal equilibrium state that doesn't know anything about this phase transition. So I can't analyze, this physics that I was talking about in terms of averaged linear observables, which are the familiar probes of phases of matter that we are more used to. So that doesn't work. To see this kind of physics, we'd have to somehow measure something like the entropy of one particular wave function. So we have to reproduce this particular branch, for example, that I highlighted many, many times in order to be able to actually measure something like entanglement on that particular wave function. And doing this is like winning the lottery, right? You have to exponentially many wave functions. You have to make the same one many times. That is just like exceedingly unlikely and becomes, prohibitive as soon as you have a many-body system with more than a handful of, qubits, a handful of measurements, right? So this is not going to scale very well, okay? Which poses, seemingly an obstruction to actually seeing this type of physics in reality, in any kind of experiment. Now, this was noted kind of early on in the very first papers in 2018, but the outlook on the feasibility of these experiments changed a bit with this other paper by Gallans and Hughes again, a couple of years later, which made the following point, which is that if we are characterizing these phases by the presence or absence of information on the initial state, as this is the point of view again of dynamical purification, is there memory of the initial state or not? So if we are taking that point of view, then in the phase in which there is information, we should in principle be able to extract that information. So in particular, think of it the following way. There is this quantum state rho that I'm sketching here, these atoms, it's some kind of quantum computer that has an initial state. It goes through this process. Let's not look at this box here for the moment. It goes through this process with unitary evolution and measurements, and then the experimentalist writes down all the measurement outcomes on her lab notebook, just keeps track of all these measurement outcomes. The idea is that if the information is in there, then in principle, you should be able to take it out by doing a suitable operation that we can call decoding, in which you take all of this information, this measurement record M that you have collected along the way, you do a computation, and you figure out some correcting operation, some unitary U parameterized by M that you have computed, that takes whatever state you have and tries to extract rho or whatever is left of it. So for example, it might place it in some of the qubits or make it easy to recover in some way. And then it is that after this process, after this feedback on the system, you would then be able to make a standard measurement and just average over all the trajectories, use all of them. And so you don't have to win the lottery. You can just do this reliably many times and get whatever, get some order parameter that tells you about the phase transition. Okay. Now the details of how this works can get complicated, but this is basically inspired by quantum error correction, where a similar thing happens. You collect data from these measurements over the course of dynamics, and then based on the data, you make a correction operation that tries to, recover the state that you had at the beginning. Now, I should also say that as shown here, this is a little bit unrealistic for experiment, because what this is saying is, do an experiment, collect all this data, do some potentially lengthy classical computation, and then go back to the processor and do something else. But, in the meantime, with the coherence times we have at present, milliseconds, microseconds, maybe, I don't know. This is unrealistic, right? By the time you do this computation and come back, your quantum computer will have completely decohered and you won't be able to do anything about it. So a further step sort of conceptually to make this more realistic was to develop so-called hybrid quantum classical or preparameters, where this quantum feedback step is replaced by classical post-processing. So the experiment actually ends at this dashed line here. We measure everything at that moment, and then this decoding happens later, and it happens purely classically. Okay, so that lets you actually get signatures of this phase transition, again, in a scalable way, in principle. And I believe this is what Sam Garrett presented on previously in this seminar series. And I'm not directly going to talk about it because we'll take a different point of view. But just before I move on to that, I just want to emphasize that this can actually be done in experiment. And in fact, it's been done now a couple of times. Most recently on this experiment that I collaborated on with Google Quantum AI, where we take exactly this point of view of making a bunch of measurements, sending them to a simulation, doing this decoding, and then computing some kind of cross-correlation between quantum experiment and classical simulation to get some order parameter, okay? And this and other experiments were recently also commented on in this nice article in Quantum magazine that kind of traces the story of the history of this field and how this seemingly unobservable phenomenon was actually realized in with these developments that I briefly told you about. So some nice light reading on this if you're interested. Cool, great. So that's it for the review part. Let me kind of get to the point of view that we take in this work, which is a little bit different. It's complementary in some way. So the physics is the same. Sorry.
Excuse me, before you, I know you want to go on this digression, but can you say, just in that case, a couple of sentences on what you use for that classical post-processing?
Mm-hmm. Yes. So for example, here, what we do is we mix, I guess I can't really explain the whole setup, but we make a bunch of measurements. We collect those outcomes. And then we do a simulation where we say, okay, knowing those outcomes, can we predict the conditional state, so the post-collapse state of one particular qubit, which we choose as our probe. So it's like, imagine the tip of a microscope that is trying to detect this phase, right? So that qubit plays the role of a probe, and we try to compute its conditional state. And then we compare that prediction with the experiment. So basically, we compute a cross-correlator of two bits. One is measured, one is computed in simulation. And as it turns out, this quantity here tells you about entanglement, post-measurement entanglement of this qubit. So in the two phases, there is a different behavior that we managed to see.
Yeah, I see. It looks conceptually similar to what Houston Gullens did by coupling to one qubit.
Exactly. It is trying to do that same thing without doing the feedback step, replacing it with a classical post-processing. And it's exactly based on that. Mm-hmm.
Good.
Yeah.
Go ahead.
Thank you. Yep. So that what I presented so far was what we call in our work the coding perspective. In the sense, again, it's kind of inspired by quantum error correction, tries to decode information that is in the system, and it takes the point of view that you are the experimentalist and you have this quantum state that you can manipulate and measure. Okay. Now we take a different perspective, which is what we call the learning perspective. In this perspective, you are an eavesdropper, so somebody who's not directly in control of the experiment, but you are kind of confined to this red bubble here. You only have access to these classical measurement outcomes. Okay, you can read the lab notebook, but not the experiment itself. You cannot directly measure the quantum state. So whatever happens here at the end, you cannot go in and measure that or do feedback or any of that. You're purely trying to use this classical knowledge to, again, through some kind of simulation, learn various properties of the quantum state rho that was here at the beginning that we assume you don't know. This quantum state rho is prepared by an experimentalist, Alice, and she doesn't share her knowledge with you. You only get to look at the measurement outcomes and are trying to make the most of them, right? Learn as much as you can. Okay. So this is a complementary kind of point of view. The idea, very informally and non-rigorously, is that the information should be, the information about the state of rho should be in one of two places. So either it's still in the system, so you can decode it and do what I said before, but then you shouldn't be able to learn anything from these measurements, or vice versa. If the information has left the system, then it should have leaked into the measurement outcomes, and you should be able to learn about the quantum state. Okay. So again, this is very non-rigorous, just kind of at the level of heuristics, but there is, this motivates an expectation that there should be a phase transition here in your ability to learn from these measurement outcomes that should go in the kind of reverse order relative to the standard, perspective we take on the transition, which is that you should succeed at learning in a phase with frequent measurements, and you should fail to learn in a phase with infrequent measurements. Okay. So the question then is, so far so good, we can certainly have this expectation, but how do we quantify someone's ability to learn, right? And we want to be able to put some sharp, statements and some math on it. And here, this brings the second idea that I promised at the beginning, that we kind of combine with this idea of monitor dynamics, which is classical shadows. And this also is a rather recent development from quantum information and quantum computer science theory. So I'll review that as well very briefly. Won't really do it justice. There is kind of a rich literature at this point, but I'll try to give the main idea, which is that we are trying to learn many properties of an unknown quantum state from a small number of measurements. Okay, and these measurements are randomized in the sense that we are taking the point of view that we don't know in advance what we care about. We just kind of generically want a description of the state, no particular observable in mind. So the best we can do is to measure in a randomized basis, right? And doing so builds a compressed classical description of the state that we obtain from doing these measurements and collecting those outcomes and then doing some computation with them. And with this description, we can actually later on we can learn many things. Okay, so the perspective here is to measure first and ask questions later. Okay, that's kind of the slogan for this type of approach. So more concretely, what are we doing here? We have this quantum state rho that we don't know. Okay, the whole point of this is to learn about it. So we don't know. Maybe somebody has prepared it. Maybe we prepared it, but we're not confident in what we did. We want to benchmark and make sure that we got the correct state. Any of these cases. And what we do is we measure it in a random basis. So we can always think of measurement in a random basis as if we're doing first a random unitary, which is a random change of basis, that's this box here, and then a standard measurement in a computational basis. And so if we do that, we get bit string, a string of ones and zeros, that we can then feed into our classical simulation along with the basis choice. So we chose a basis, which is this unitary U, and then we got an outcome B. And then we try to make our best educated guess as to what the state rho might have been, before we did all of this. And if you think about it, there is a very kind of naive and simple answer to this, which is that, if we are trying to guess the state right before these measurements, so right here where I'm indicating, then we have nothing better to say than just the projector on the bit string B. Whatever we just measured, that's our best guess for what the state was, right, in the absence of any other priors. And then we have to rotate this guess back to the original basis. So we have made this rotation U, so what we do is we undo it. We apply U dagger to our measured bit string state. Okay, and this projector we obtain is our best guess for the state rho. This is what we call the snapshot of the quantum state. Okay, so this again is computed classically. So this application of U dagger is all done in simulation. And then, okay, this by itself is not a very good guess for the state rho because, for example, this is a rank 1 projector. It's a pure state. Maybe rho was a full rank density matrix. We're not necessarily getting something very close to it. But it has a little bit of information about it. And we can, aggregate many iterations of this experiment, of this protocol, and average all of these snapshots. And what we get is written here. So if you think about it, it's some kind of weighted average of these snapshots, weighted by the Born probability of measuring that particular outcome. And this is you can check that it's in fact a state, and it is a linear, it depends linearly on rho. So this, for those of you who know the QI quantum information jargon, this is a quantum channel. Okay, so it's some kind of evolution applied to rho. Okay, and then because we want to actually predict properties of rho, we can again in classical simulation try to undo the effect of this quantum channel M by applying this inverse map to our snapshots one by one. And if we do that, we get something that we can call the, this rho hat, we can call it the classical shadow, or, one classical shadow of rho. And by definition, by construction, these classical shadows are on average, the true state. Okay, if you plug in this definition in here and you take the average through M inverse by linearity, you'll find that this is M inverse applied to M of rho. So you get these cancel out and you get rho. Okay, so Okay, so we've produced basically these quantities that we can call unbiased estimators of rho in the sense that they replicate rho on average. And now from these, we can make predictions about various properties, for example, expectation values, entropies, fidelities, various things about the quantum state rho. Okay, now.
Matteo,
Yes.
I have a question. So the randomized measurements, are those done experimentally, or are you, maybe I missed the step.
Right. Thanks for, yeah, it's good to clarify. So in this protocol, this part here is done on a quantum.
Okay, so the experimentally, what you have are computational basis measurement, but you're going to turn that into a randomized measurement by doing this.
So the randomized measurement is done in experiment. So you have to define an ensemble of random unitaries, and then of course some of them are easier to do in experiments, some are not very realistic, but certainly single qubit random notations are okay. They're done routinely on for example Google's experiments, or other such cases where you measure entropy. They're typically done this way. You make randomized rotations of single qubits, and then you measure them in a computational basis. And then there is some post-processing that happens to get the entropy. But yeah, just to clarify further, this part here is done on the processor. And then, on this side, this is all simulation. It's all happening classically. Thank you for clarifying. Yeah. Great.
So your simulatability probably restricts what type of random unitary you choose, right?
Exactly.
Is it like all Clifford or something?
Exactly. So in this original paper by Robert Huang and Richard Kung and Jean Praskill, they proposed two ensembles that are tractable analytically and very easy to do. One is single qubit random Cliffords, and the other one is many-body random Cliffords. But so Clifford is useful for simulation, and then again, this kind of a one body or many body is also helpful, makes things easier. If you had something in between that's kind of somewhat local, but not completely, then things get a little harder. It can be done still, but it takes a little more work. So anyway, there's lots more recent works trying to do different ensembles of random unitaries, but those are the two standard ones: single qubit Cliffords and many-body Cliffords. Yeah. Okay, but that is a very important point that we actually will not deal with at all in this work. So the classical efficiency of simulation, we forget about it. We're trying to quantify the quantum sample complexity, so number of experiments needed, if we are granted kind of infinite classical computing power. Okay, and then it's a very important and interesting question for the future to, how does this change if we actually restrict to finite resources? But we won't talk about this today. Okay. All right, so back to our eavesdropper problem. The idea is that now Eve, so this eavesdropper character, is trying to use classical shadows to learn properties about the quantum state rho. Okay, and then within classical shadows, there are various ways of quantifying, the ability to learn. In particular, there are quantities you can compute that tell you how many experiments you need to learn a given quantity within accuracy epsilon. Right, so that's what we're after. But before we can use classical shadows, there are a couple of important modifications that have to be made here to accommodate the fact that the setting we had in mind before and the one we had in mind now are different. In particular, before we had the ability to make this complete measurement at the end. So this bit string B was a complete measurement of the final state, which we now don't have. So we'll have to replace that with something else that doesn't take any knowledge. Okay, so let's say what? And the second thing is that, in the standard protocol, we take this final state and we rewind it, we turn it back in time with the application of U-dagger, so the inverse rotation. But in this case, the time evolution itself is not unitary. It's some trajectory parameterized by M, which is some string of outcomes, of a monitored evolution. So again, we have to figure out how to, use this in place of the unitary evolution. And so to summarize the similarities and differences, we can look at these two diagrams. And by the way, this diagram here on the right is taken from the paper by Iju and Yu and collaborators, which is studying a similar problem as us, comes to similar results, but has nicer figures. So I'm stealing their figure here. But anyway, the idea again to recap is that we have a quantum experiment where time is going vertically in this diagram. Then we take this classical data, we pass it to our simulation, and then our simulation is doing this kind of time reversed evolution, right? It's taking this final state and trying to rewind it with the application of UDagger to prepare some classical snapshot. And the idea is to try and do the same thing in our new setting, right? Where we don't have access to this final state, and we have these mid-circuit measurements. But it is the same. We have this forward in time step, which is done on the quantum processor. We then pass this information to the simulation, again, with this measurement record that here they call it B, we're calling it M. And then we try to undo the time evolution. And the idea is that if we don't know anything about this final state, then in some sense, the best we can do is to have a flat prior, just guess a completely random state, which means a maximally mixed state proportional to the identity, and just place that completely mixed state here at the final time, and then evolve it backward with this quantum trajectory for the monitored evolution. So if you do that, then you get the backward evolution K dagger acting on the identity, and then by conjugation K on the other side. Okay, so simply you get K dagger K, and then you have to trace normalize to get a state. Okay, so this is our snapshot for each measurement sequence M. Okay, so this is all to say, this was the standard prescription from classical shadows. This is the protocol that we propose. In fact, one of the protocols. We've got a few more depending on what you want to optimize, but this is kind of more intuitive one. Okay, that Eve can use to make a guess about the quantum state rho. Okay. All right, so now, having defined these snapshots, we can go through the whole machinery of classical shadows, which I will spare you. But the important point is that there is an emergent ensemble of quantum trajectories that are defined purely based on these operators, these quantum trajectories of the evolution, Km, K dagger M. Okay, so as I was saying, we define these snapshots, which are states, and then with each one of these states, we also have a probability, which is defined this way, that again pops up as part of the protocol. So kind of mathematically it emerges from that description. And this again is a collection of states with probabilities. So it's a state ensemble. Okay, so it's a distribution of probability over states. And important to note also that it is not the actual distribution of states that arise in the experiment, because those know about rho. Those are actually something like K rho K dagger, right? So it's not that. It's an emergent distribution that comes out purely from the description of this learning strategy that Eve is applying. Okay. But then, as it turns out, the success of the protocol depends on properties of this particular ensemble of trajectories, which we can see they are basically these backward evolutions of a completely mixed state through this quantum circuit that features both unitary gates and measurements. And so we are within that framework of dynamical purification that I mentioned at the beginning, towards the beginning of my talk, right? Where this mixed state that we send in, may or may not become pure depending on the measurement rate. There is this so-called dynamical purification phase transition.
Just clarify, I'm assuming
Yep.
it's the case, the complete architecture of the circuit. That is, the location and nature of every single gate and where they are with respect to your measurements.
Yes,
Okay.
I did not say that. That's a great point. Should have emphasized that. You have complete classical knowledge of what is happening during this evolution. So, maybe you're not just peeking at maybe the lab notebook also includes the blueprint of all of these circuits, what all the gates are, where all the measurements are happening, and then what their outcomes are. Because you use all of this knowledge to make up these states and these probabilities. Yeah, great point. So as it turns out, again, kind of non-obviously, from doing the math, the success or failure of this learning protocol is determined basically by properties of this measurement ensemble, and in particular, the average purity of this ensemble of mixed states. So defined here. So it's this sum with a pi of m. This is just a weighted mean. It's a sum of the trajectories weighted by the probability. And then trace of sigma squared is the purity. So it's a quantity that tells you if the state is pure or not. It's 1 for a pure state, less than 1 for a mixed state. And this, average purity, again, is related to a second Rayleigh entropy. So it has to do with entanglement. And it defines this dynamical purification phase transition by the value of this entropy density here. So if we take this quantity, we express it in this way as e to the minus some coefficient times system size. The value of this coefficient is what determines these phases. And we have, as I was saying, we have these two phases. At frequent measurement, this density becomes 0, and then at infrequent measurement, the density becomes greater than 0. And then what we show essentially, the key result of our work is that this phase transition maps onto a transition in the eavesdropper's ability to learn about the state, in the sense that in this phase, frequent measurement, we have what we might call kind of qualitatively efficient learning, in the sense that it's just about as good as if you were able to do final measurements on the state, if you had actual access to the quantum processor. So in a way, you're extracting all of the information that you might extract. On the other hand, below this threshold.
Question. So do I understand it correctly that you're taking this you're sort of backwards propagating in time on your quantum, classical computer?
It is on a classical computer,
right? So the fact that you can backwards propagate means you can also probably forward propagate, meaning you can do the whole thing all on the classical computer.
Right.
You didn't need a quantum processor to do this.
Yes, you could have simulated the whole thing. Yes.
Okay, so then you can compare what you get by doing the whole thing on a classical computer with more expensive version of doing half on a quantum processor. Have you done that?
We haven't done that. It would be interesting to do that, but certainly, yes, you can have, these order parameters. So I'll say also a little bit in a moment, this defines another type of quantum classical order parameter, but you can always compare those to just classical, right? Just purely simulated. And that typically, so we didn't do, we did something similar in the experiment that I mentioned earlier, which was before this paper. So slightly different, but there too, you can compare your quantum classical parameter, which is purely simulated parameter, and you might get interesting stuff from the effect of noise, because obviously the noise is only in the experiment, and it actually shows up in an interesting way. So that's more interesting, as opposed to trying to get the same thing, which you can try, but
What is the definition of interesting? Does your PC move to the left or to the right? It looks like there's only one outcome.
Interesting, yes. So technically, with a finite noise rate, so it's a matter of order of limits. So if you make your noise rate finite and then you push the system size, you will get a trivial phase everywhere. Trivial, I guess, would mean volume law, but volume law in the boring sense that it's a mixed state. So it just has a lot of entanglement with the environment. However, we are in a regime in that experiment where the system size and the noise rate are kind of both comparably large to small. So we actually get the susceptibility to noise that becomes itself an order parameter for the phase transition. So that becomes a little technical to explain without a slide on that, but it's what
if there isn't a phase transition in a thermodynamic limit, how do you define a phase transition on a finite size system?
Right. So you're seeing kind of transient signatures of the transition that would be there if you could take the other thermodynamic limit. So noise is so system size going to infinity first, and I'm sorry, vice versa. Noise going to 0 first, and then system size going to infinity. Then you would get a sharp signature of the phase. And then it's just a matter of numbers, kind of where you are in this transient regime where both the size and the noise are finite.
So in reality, it will be a crossover.
In reality, it will be a crossover, yeah.
Okay, thank you.
Yeah, that's.
I'm a little perplexed about two things. I'll just ask both questions. Number one, I'm not quite sure what's happening as the measurement rate increases and you've got, sort of this flat line. And so related to that is two of the standard features of classical shadows are, number one, the number of shadows you need to use is independent of the size of the system, that is the number of qubits.
Right.
And secondly, the number of operator expectation values you can learn to, some accuracy, of course, goes logarithmically in that number of measurements. So I'm wondering if that's related to my first concern, and how those two features of classical shadows manifest themselves here.
Right. Yes. Good. So what you see here is basically saying that. So let me say this first. So if you set p to be equal to 1, so we are sitting at this extreme point. Let me go back to a plot here, right? So to this diagram, that would mean that you have measurements everywhere in this circuit, right? At every single qubit, at every single time step. And so in particular, in the very first time step, you have something that looks exactly like the standard classical shadows protocol, where you're just doing a complete measurement on the system. And then whatever happens later is at that point useless because you have already projected out your state, right? But so that p equals to 1 point is exactly the kind of textbook, HKP classical shadows protocol, right? What this plot is saying is that qualitatively, up to kind of order 1 numbers, that same protocol keeps working in the same way throughout this phase. So even if you're not making this complete measurement, measuring quite exactly everything, but maybe half of it, and then, the other half kind of slightly later on, the qualitative behavior remains the same. Below the threshold, that's what I was going to say next, but basically things become exponentially less efficient. So actually the performance of shadows then becomes, deteriorates exponentially with system size. In other words, the system is trying very hard to hide the information, and it becomes better and better at doing that as it gets bigger. So then things change, okay? But this is precisely this phase transition between these two regimes. So I don't know if that answers completely your question. But maybe more will be clarified. I mean, by the way, I'm almost done. I guess I'm almost at the cutoff, but don't have much.
You have 5 more minutes.
Excellent. Yeah, I'll just flash some results. Let me just skip this. Okay. Okay. So we do basically. So there are subtleties with locality which you don't really want to deal with at this stage. So we do an encoding step that applies basically a hard random unitary to the whole system, and this completely washes out the effects of locality. Okay, so we can just forget about it, and it simplifies our analytical. The whole treatment of the problem becomes much easier because of this, and we can solve lots of things exactly. So in this framework, we show the following. Oh, by the way, for those of you who are experts, this means that at this point, we're looking at essentially globally randomized classical shadows. So that's the thing to have in mind at this point is globally randomized classical shadows as a comparison point. So we analyzed basically how well we can learn different interesting things about a quantum state. The first one is Pauli expectation values. This is kind of a natural thing to want to know for many things, from variational algorithms and many other applications. We show that the sample complexity here undergoes this sharp change, but it is exponential on both sides. So it is basically 2 to the n in the so-called easy phase, in the phase of efficient learning, and then it transitions non-analytically at this critical point to something that scales as 2 to the n to some power greater than 1. This power is 1 plus s, where s is the entropy density, which is the order parameter of that entangling phase, which again sets in non-analytically at this point. So things become exponentially harder in the kind of low measurement phase, but they were already hard to begin with. So this is not maybe such a qualitative phase transition. We get something more drastic if we focus on a different observable, which is the many-body fidelity. So you take a particular quantum state, pure state phi, and we take the expectation value rho on this projector on phi. Okay, so this is the fidelity between rho and this pure state phi. And we can estimate this with classical shadows. And in this case, we get actually that the sample complexity goes from constant or at least sub-exponential, right, with this entropy density 0. And then it transitions abruptly to exponential below the threshold. So we start to actually fail to learn below this phase transition. And last thing we look at is an application to systems with asymmetry, where this was kind of pioneered in these works on systems with a U1 symmetry, where you're trying to learn the value of a conserved charge. So there is a U1 charge, number of particles, for example, that is conserved, and you're measuring the local charge density and trying to guess the value of the total charge. And so this was analyzed in a couple of very nice papers in the last year or two. And here the nice thing is that we don't have to think about this very hard. We can just apply our same prescription, for this kind of eavesdropper shadows, and we get again a phase transition corresponding to the same phenomenon called a charge sharpening transition, just a separate transition from the one that we mainly talked about. But here the transition is between two polynomials. So we've seen all kinds, like two exponentials, polynomial to exponential, and now polynomial to polynomial, but with a kind of a factor of system size difference between the two sides. So we again, learning becomes harder, but only by a polynomial amount in this case. Okay, last thing I want to say, other than summarizing these different results we found, is that all of these, your ability or inability to learn in these two phases actually itself gives you an order parameter, in the sense that we have recipes for these estimators of these various quantities, which we can calculate, and they fall on some range, right? And in the phase where we are unable to learn, or it becomes expensive to learn, that's because the variance of the estimator is huge, exponential in system size, whereas the actual value, for example, of fidelity, is of order 1. So fidelity is between 0 and 1, right? So if we are trying to, if we have this kind of spread in our estimators, and the quantity we want to learn is actually, containing a tiny, tiny range near the center, we'll have to reduce this variance by collecting a catastrophic number of samples, right? So that's why we fail. However, actually estimating the variance itself is straightforward. You just need order 1 data points, and you get some pretty good estimate of the variance. So that variance itself can actually serve as one of these quantum classical order parameters for the phase transition. And of course, as we already mentioned in passing earlier, the really big outstanding question is, what is the classical simulation complexity of all of these things I talked about? Because we are focusing exclusively on the complexity of quantum experiments, so how many experimental shots we need, but we're assuming infinite classical computing time or power, right? So if we actually put restrictions on that, then does this change kind of gradually or abruptly collapses to complete inability to learn, right? So that's really the main outstanding question. With that, I'll just flash my conclusions and be happy to take any more questions, even though we already had a good number. So thank you.
Are you going to organize?
Oh, any questions?
Hey, Matteo. Can you hear me?
Yes, I can hear.
Oh, yeah. Just trying to confirm one thing. So your P sharp in your formulation is at the same location as the charge sharpening transition, or is some other new phenomenon?
No, it is exactly the charge sharpening transition.
Same thing. Okay.
The same one. Yes.
I see. And then I guess you do something tailored to the charge, so you don't see the next entanglement transition. Is that how I should read the plot?
So the plot here is essentially we are asking. So in all of these plots, what I'm plotting is the so-called shadow norm of something. Shadow norm is just the number of samples needed to learn that thing, and it happens to be a norm. So in the videos, for the case of Pauli's, that was shadow norms of Pauli operators. For fidelity, it was shadow norm of a projector. For this case, it's shadow norm of the charge operator. So for that particular shadow norm, it doesn't feel the entanglement transition, it only feels the charge sharpening transition.
I see. So maybe you could also devise something that only feels the second one, but not the first one. Is that, or maybe I'm not sure.
Probably there is a subtlety there, which is that going back to the definition of a shadow channel. So this channel M that you're trying to invert as part of your post-processing, for dynamics with a U1 symmetry or really any other symmetry, this becomes non-invertible. And that's because of the symmetry. So if you have any quantity that is off diagonal in the symmetry, for example, a raising operator, that gets annihilated by the channel. So if you try to then go in and do M inverse, you get an infinity, right? So you have to restrict to operators within the charge blocks. So the charge is okay, of course, it's diagonal. Other things will be okay within the charge blocks, and those could fill the entanglement transition. But if you're just kind of naively applying the thing to the whole Hilbert space, you'll just get singularities, right? Or at least this will be ill-defined.
Thank you.
Mm-hmm.
If I understand your comments at the end correctly, you were asking about what is the time complexity of determining the learnability, and whether it's polynomial or exponential. You didn't say anything about the space complexity. I'm assuming you're still, the reason we use Clifford simulations in this case is because otherwise these shadows would be require exponential space. Using the Clifford simulations means that we can calculate these expectation values only using a polynomial space in the number of qubits. Is that something you've also considered, or you're just always going to be in this Clifford space?
Right, that is a very, very good point about the space. In fact, even just the complexity of storing these shots in memory, like just the U itself in memory, the space complexity comes first, I guess, before even the time complexity of doing this operation. So we, for the most part in this work, we don't think about either space or time complexity. We assume we have kind of infinite space and time. And we think only about the sample complexity of the experiment, right? So that has this sharp phase transition. So one thing that is known from one of these prior works on the charge problem, for instance, is that if you, believe in this plot, it might be this P success. If you apply a polynomial time decoder, you still have a phase transition, but it's not the sort of ideal charge sharpening transition. It's a little bit further out, right? And then in principle, with more and more computing resources, you could move this critical point all the way to this kind of asymptotic limit. I would believe that the same thing should happen with the space complexity as well. A thing that's probably sort of a bound that you can probably put on this is that there is this critical P that is typically somewhere around 16% in standard models, but there is also a different transition, which is a percolation transition that happens at, again, that depends, but in these models, it happens at 50%. As you might imagine, if you do more than if you measure more than half of the bonds in this kind of diagram, you just break it down into disconnected pieces. So in that case, I'm fairly sure you can succeed with polynomial space and time, but that is quite far from the kind of asymptotic transition, right? It's whether you can do much better than that, I really don't know. It would be very interesting to find out.
Great.
Mm-hmm.
More questions? No, okay, I have a question. Have you observed any finite size kind of behavior in any other transition?
So the only kind of finite size data that we collected for this was this part that I skipped because it gets into a little bit of details that I didn't want to get into. But this is about the Pauli expectation values, right? And there is a kind of interesting trade-off here that happens. This is in the case in which you're not doing this pre-scrambling step. So you're just diving right into the monitor dynamics. And so it becomes possible to have measurements right on the state right away. And then you're very sensitive to locality. So we see this kind of non-monotonic behavior where the measurement-induced phase transition, which I mentioned was around 16%, that is basically where this minimum is. We see it come out as an optimum between two things that happen. So below PC, just everything becomes hard, kind of as expected. So these curves kind of take off. And then above PC, you are kind of aware of locality, and locality plays a weird trick in the sense that it makes it easy to learn small operators, but very, very hard to learn the big ones. Actually worse than it would be if you just did a random unitary on everything. So you get this broad distribution between here. There are different means that are shown. Okay, so this is to get to the interesting finite size bit that we get here is that not shown here, but the actual scaling with system size of this minimum that we get appears to be close to 2 to the n, which is also consistent roughly with what is found in the other paper. Sorry, this paper. Yeah, each one's paper. There they find, they look at a slightly different thing. They find maybe 2 to the 2 point something to the power of n, slightly larger than that. But anyway, 2 to the n is an optimum, kind of conceptually. We know that there's a lower bound, that you can't learn these operators better than 2 to the n. And so it looks like, and the interesting finite size thing we see there is that the measurement-induced phase transition seems to be either optimal or nearly optimal for learning these operators. But yeah, if that is addresses your question, but.
Okay, thank you. All right. You can stop.
Thank you so much.